So I have a couple theorems for you. Number one, Rolle's theorem. Now I'm going to leave the proofs for you to read in the textbook, but here goes. If I got a function f that's continuous over a closed interval from a to b, differentiable over the corresponding open interval from a to b, and if the corresponding y values in the graph are the same at a and b, like for example, how about this pretty picture? It simply means that there's a value of x somewhere between a and b for which the tangent line is horizontal. So Rolle's theorem's conclusion is that there exists a value of x, call it c, strictly between a and b, such that the slope of the tangent line at that value of x I called c is 0. Now notice how in the example I just made up, it happens to be the case at another value of x, that's fine. Here too the tangent line is horizontal. It's just that Rolle's theorem guarantees me at least one value of x I called c in this open interval, for which that's true, but remember, I have these two conditions that have to be met. Now the reason why those conditions have to be met is because they're not. Let me remove one of the conditions. How about continuity? If there's no continuity, then notice how my curve could behave as such. And it could be the case that for no values of x between a and b is a tangent line horizontal if I'm not guaranteed continuity. I think likewise, if I'm not guaranteed differentiability, maybe something like this happens. Here's a value of x between a and b for which I'm not differentiable right there, because I've got a little cusp in the graph. And therefore, notice how I don't have a value of x between a and b for which tangent line is horizontal. It might be the case that I do have one, I'm just not guaranteed it under Rolle's theorem. Now, typically I would say the utility or usefulness in Rolle's theorem is to be able to prove the mean value theorem. It's sort of like a higher level of Rolle's theorem. So very much like Rolle's theorem, if I'm guaranteed continuity and differentiability over the interval from a to b, first closed then open, then there exists a value of x between a and b for which something interesting happens. Before I actually state it, can I just show you in the pretty picture? So f of a and f of b are not necessarily the same, and maybe my curve does something like this. Now, what this mean value theorem says is the following. There is indeed a secant line passed through this point right here in blue. If you can read it, let me look at my computer screen. Oh, I hope it's okay. That says a comma f of a. Here's another point on the graph of f, b comma f of b. Now, if I'm guaranteed continuity and differentiability over the interval from a to b, first closed then open, it basically means there's some value of x in between a and b for which the tangent line at that new value of x, I'll call it c, is the same as, or has the same slope as, the secant line passed through the endpoints. I hope I said that sufficiently. I'll say it again in case I didn't say it very clearly. If I've got these two conditions being met, then I'm guaranteed that when you take a peek at the slope of the secant line passed through these 2 points, its value is going to be the same as the slope of the tangent line at some value of x between a and b. Or shall I say more symbolically, there exists a c between a and b strictly such that the slope of the tangent line there is indeed equal to the slope of the secant line passing through those 2 endpoints. Here's the conclusion of the mean value theorem. Now, I'm not going to be able to sit here and give you some sophisticated applications to the mean value theorem, but maybe I'll talk about it algebraically. The big point behind the mean value theorem is that actually something I use to prove in other theorems. Now, given that this is an online course, I am spending some time, or taking away some time on proofs and relegating them for you to read in the textbook. But how about if I say this? You know, the only decent application I really can come up with is when I look in biology. And I can talk about maybe how a population is changing just by looking at the changes in births and the changes in deaths. There I can kind of mimic some kind of application of mean value theorem, but I'm very restricted in terms of applications of mean value theorem. Again, it's mostly used for theoretical results further on